we will begin our study towards looking at this very important device which is the metal oxide semiconductor field effect transistor. And this device is quite important because it is the building block of all modern day integrated circuits. Okay. And before we get to understanding all the details regarding MOSFETs, we will initiate our study on something called as the MOS capacitor, that is a metal oxide semiconductor capacitor. Now MOSFETs itself, I mean, there are, generally speaking, there are two kinds, you could say. Okay. So you have two modes of operation. One is the depletion MOSFET, okay, which is built a little differently from something called as the enhancement mode MOSFET. Okay. The focus of our study is going to be the enhancement mode MOSFET, and before we start this, we will look at the MOS capacitor. So the MOS capacitor has got a structure of as shown here. So you have a gate metal, you have an insulator or an oxide, you have a semiconductor, and you have a contact to the semiconductor. So this gate metal is your control terminal of your MOSFET when you talk about sending a signal from A to B. Okay. So we have not yet built the MOSFET here. So this is just the MOS capacitor. So what you see is just a capacitor circuit. So this gate metal is given a gate voltage Vg, which is measured with respect to the reference. Then the reference contact is the back contact here. So here we have set the reference contact to ground, and this Vg is with respect to ground. So Vg is the gate voltage provided to the gate metal, and then the gate metal sandwiches an insulator is sandwiched between the gate metal and the semiconductor. Okay. So this is a very key difference. So which means that if this insulator is an ideal insulator, there is no current flowing from the gate to the semiconductor. So this current is ideally 0 at low frequencies. Okay. So you have a gate metal and you have an insulator. Now since this insulator, in the case of silicon technology, since the most commonly used insulator is silicon oxide or some other oxide, the insulator is also called as an oxide layer. Okay. So that is why you have this name metal oxide semiconductor. A good equivalent name is metal insulator semiconductor. And the insulator sits on top of a semiconductor, and this semiconductor is lightly doped either P or N type. Okay. But in this case, for our example and for this study, we will consider a P doped semiconductor. So you have the gate, insulator, semiconductor, and back contact or the reference terminal, which provides not only the voltage reference, but which also supplies this semiconductor layer with an infinite source of carriers. Okay. So this is the structure that we will be looking at and that we will analyze for some time. Now as usual, let us start looking at the band bending diagram. Okay. So let us say we are going to take the metal, the gate metal. We will not worry about this back contact, we will just assume it is an ideal ohmic contact, not worry so much about it, because everything that is interesting with regards to this device and with regards to the study happens here at the insulator semiconductor interface. So this is the region of interest, okay, because that is where the junction is. Okay. So we are basically creating a junction. Since we have looked at junctions of typically all our junctions have been a metal semiconductor junction or a PN junction, but here you are looking at a gate insulator and an insulator semiconductor junction. Okay. So since this is our region of interest, all our focus will lie in this particular region. So, let us draw the band diagram. So, I have just thrown in some numbers here just to give you a feel for some typical values. So, we have three different structures. So, first let us say this is the gate, this is the gate metal. So, we have chosen a metal whose work function is 4.1 electron volts. This is the insulator or the oxide, and we have chosen an oxide or an insulator whose band gap is about 8 electron volts. So, it is a large band gap. So, that is the conduction band, that is the valence band, and that is a large band gap in the insulator. And the electron affinity of the insulator. Okay. So, the electron affinity for the insulator is about 0.95 electron volt. So, the electron affinity has to be a constant and is irrespective of what kind of junction you create or what bias you apply, etc. And similarly, the work function for a metal is a constant. Once you pick a metal, you pick the work function. And then finally, you have your semiconductor. Okay. So, we have not yet created the junction in this diagram. So, we have the semiconductor, and here you have some band gap. So, for example, let us say the band gap is about if you take silicon, it is about 1.12 electron volt. Okay. We have some band gap, and the semiconductor is doped p type, which means that the Fermi level of the semiconductor lies a little below mid gap. Okay. It is closer to the valence band edge as compared to the conduction band edge because it is doped p type, and the work function of the semiconductor is the difference between the vacuum energy level and the Fermi level of the semiconductor, and that is about 4.9 electron volt. So, that is what we have chosen. So, these numbers are just examples. I mean, these are not the only numbers that you have to use. I hope that is obvious. And the electron affinity of the semiconductor is again a constant. So, once you pick the semiconductor, you have picked the electron affinity, and let us say the electron affinity is about 4.05 electron volts. And now we are going to create a junction. So, when you create the junction, the work function of the metal will not change, the electron affinity of the insulator will not change, and the electron affinity of the semiconductor will not change, and if it is a thermal equilibrium, the Fermi level will align. Okay. So, let us say we have now created the junction. We have brought these three pieces together and we have now created a junction, and that junction is shown in this figure here. So, what happens? So, here you have the metal. Firstly, the Fermi levels have aligned. The metal Fermi level is the same position as the semiconductor Fermi level. Okay. And since there was some work function difference between the metal and the semiconductor, in order to align these two Fermi levels, there has to be some residual voltages, okay, because charge has been transferred, and in this case charge has been transferred from the metal to the semiconductor. So, here is an interesting question. So far we have, whenever we did a band diagram at thermal equilibrium, let us say it is a PN junction or a metal semiconductor junction, we said that the Fermi levels align at thermal equilibrium, and the Fermi levels align because of the charge transfer. And very early on we looked at some very poetic analogies like water in a bucket. So, you have these two buckets and you have less water here and more water here, and this corresponds to a Fermi level that was higher or work function that was lower, whereas this corresponds to a work function that is higher, and when you merge these two buckets, the water flows from there to here, thereby aligning the Fermi levels. Okay, so we looked at all these analogies and we had a mathematical derivation of why the Fermi levels should align at thermal equilibrium, because the flux of the carriers have to be balanced. But here is the question. So, for the Fermi levels to align, you need to have charge transfer. Like for example, in this case electrons are moved from the metal to the semiconductor, but you now have an insulator sitting in the middle. So, the question is, how did the charge transfer? Okay, so, there is something for you to think about. but let us just say that the charge did transfer and the Fermi levels have aligned, and this is a reasonably good assumption. Okay. So, the metal has transferred electrons to the semiconductor, which means there is going to be some band bending in the semiconductor. But since there is also an insulator, the driving force for any band bending, which is the metal semiconductor work function difference, leads to not only a built in potential in the semiconductor, but also a potential across the insulator or the oxide. So, this difference in the metal and semiconductor work functions is the driving force for the band bending, and this difference is split between the built in potential of the semiconductor and the voltage drop across the oxide. But then what else do you see here? So, since at this edge, now let us come to this particular edge. Okay, let us come to the gate metal insulator interface. So, you see this barrier here. Now, since at this point the electron affinity of the insulator was about 0.95 electron volt, and the electron affinity of the semiconductor of the gate or the work function of the gate metal at this point is 4.1 electron volt. So, that is 4.1 electron volt, and therefore, since these two are constants, this barrier height has to have a value that is the difference of these two energies, and that is going to be about 3.15 electron volt. So, similarly you can do the same thing for the semiconductor insulator interface. The semiconductor, so if you look at this particular point here where the conduction band is meeting the insulator, at that particular point the semiconductor has got an electron affinity of 4.05 electron volt. The insulator has an electron affinity of 0.95 electron volt, and therefore, this barrier is going to be the difference of those two energies, and it is going to be about 3.1 electron volt. And this work function difference, that is if you think of it in voltages. So, we have removed the Q here. So, we are looking at the voltages now. This work function difference, which is say 4.9 minus 4.1. Okay. So, that work function difference, so in this case the work function of the semiconductor is larger. So, let us say, or let us just instead of using negative signs, let us just say it is 5 ms. Let us just take the modulus of all this. Okay. So, this work function difference has led to a drop of Vox across the oxide. So, that is why you see that there is some electric field in the oxide, okay. And the remaining, which is 0.8 electron volt minus Q Vox, is the energy difference between the bulk conduction band and the point where the conduction and the point near the interface, the conduction band energy near the interface. Okay. So, this is what happens when you form the junction, when you form the metal insulator semiconductor junction. So, this is all at thermal equilibrium. So, we have formed the junction and it is all sitting at thermal equilibrium with the Fermi levels aligned, and we see that simply because of the work function difference between the metal and the semiconductor, you have all this band bending. You have an oxide that has got a built in field, you have a semiconductor with a built in field, and we can now solve Poisson's equation here and estimate the field, etc. Now, the question is, how do I not have any band bending? Okay, so, let us say I want to make all these bands flat again. Okay. So, which means that I want to get the bands back to the way they were before the junction was formed, but I want to do it when after the junction has been formed. Okay. So, I do not know if I am clear enough, but the point is, in order for me to get these bands to be flat again artificially, what I need to do is I need to apply a voltage on the gate. Okay, I need to apply a voltage on the gate, and by applying a voltage on the gate, what we are essentially doing is we are going to recreate the initial Fermi level difference. So, that is the metal work function, that is the semiconductor work function, and we want to recreate the difference of 0.8 electron volt, because the only way we are going to get the bands to be flat is if you go back to, if you get the metal and semiconductor to have a work function difference that is 0.8 electron volt. So, you want the metal to Fermi level to go up relative to the semiconductor Fermi level, and this has to be done by applying a gate voltage. So, since we are looking at in all these band diagrams we draw, it is all drawn such that the electrons run downhill and the holes like to run uphill, which implies that if I apply a positive voltage to the metal, all the energy levels will go down, and if I apply a negative voltage to the metal, the energy levels will all start moving upward. Okay. So, essentially what we need to do in this case is apply a negative voltage to the metal and shift the metal's Fermi level upward by about 0.8 electron volt. So, if you can create this difference of 0.8 electron volt between the metal and the semiconductor Fermi level, then we can get all the bands to be flat, because we have removed the cause that created all these built in potentials. So, you can see that the insulator, the bands are all flat here, the semiconductor does not have any band bending, and all the band bending has disappeared. But of course, we are now not at thermal equilibrium because we are applying a gate voltage, and therefore, the Fermi levels are not aligned at this point. And the moment you remove the gate voltage, the material will head back towards equilibrium with the metal transferring electrons to the semiconductor, and therefore, the conduction band edge near the interface will start bending towards the Fermi level in the semiconductor. Now, this gate voltage needed to create this flat band condition, okay, something called as a flat band voltage. Okay. So, this is a technical term. Okay. So, at thermal equilibrium we had some situation, it need not always be this is the situation for the numbers we have chosen. The bands could be bent the other way, it really depends on what the work function differences are, or what the work function difference is between the metal and the semiconductor. But in our particular case, the bands were bent downward, and in order to achieve flat band condition we needed to apply this gate voltage, and the gate voltage at which the bands become flat, that is the gate voltage at which there is no potential drop across the oxide and there is no built in potential in the semiconductor, is something called as the flat band voltage, and we will give it a special symbol, we will call it VFB. So, when my Vg is equal to VFB, all my bands are flat. Okay. So, in this particular case we need our VFB is definitely your phi ms, which is the work function difference between the metal and the semiconductor. It is not the work function, sorry, the work function difference divided by Q. So, we are looking at the potential here. So, VFB is the potential, it is not energy. All right. So, now let us say what happens, let us start playing with this system. Okay. So, this is our flat band condition. So, let us look at the figure on the left hand side first. So, this is our flat band condition. You see there is no banding, there is no bending of bands in the semiconductor, there is no band bending in the insulator, and that is because we have artificially applied, a gate voltage Vg which is equal to VFB, which is the flat band voltage. So, now let us say we start making Vg further, we start making Vg less than VFB. Okay. So, we have already applied a negative voltage here, we start making it more and more negative. Okay. So, let us say in this case VFB was what? VFB was minus 0.8 volts, because phi m was phi m is 4.1 electron volt, phi s is 4.9 electron volt, and phi ms, which is phi m minus phi s, is going to be minus 0.8 volts. So, that was our flat band voltage. And now we are going to make Vg less than Vfp. So, which means that let us say we start making Vg equal to minus 1 volt and then minus 2 volts, etc. So, what are we doing? So, we are further increasing this difference between the metal work function and the semiconductor work function. So, the metal Fermi level will start moving further away from the semiconductor Fermi level, and it will increase this energy gap between energy difference between these two levels. So, this means that at Vg equal to Vfp we were at flat band, and if I make it further negative, then we are again going to drift away from flat band, but in the opposite direction. Okay. So, since my Vg has now become minus 2 volts, you will find that the bands start bending the other way. Okay. So, the electric field in the oxide is going to change direction, and you are going to have band bending in this manner, and the bands in the semiconductor will start tilting upward, okay, as compared to the downward tilt it had at thermal equilibrium. It will now start bending the other way because we are making Vg less than Vfp. And when we start making Vg less than Vfp, this band bending is going to encourage all the majority carriers, since you remember this is a p type semiconductor and it has got a lot of holes. Okay. So, for example, if it is doped with dopant concentration of Na, and if all these dopants are ionized, then the whole concentration is about Na, if Na is much greater than the intrinsic carrier concentration. So, plenty of holes, and these holes are going to start running up the hill and they are going to accumulate at the interface. So, as I make Vg, as I continue making Vg less than Vfp, we are going to encourage holes to appear at the interface. Now, let us go the other way around. So, let us say we head back to our flat band condition, and the way we go back is we start bringing this voltage higher and we make it equal to Vfp. So, let us say we are back at flat band, and now we start taking Vg the other way around. So, we make Vg greater than Vfp. Okay. Now, as you start making Vg greater than Vfp, the Fermi level of the metal will start moving downward, okay, and we will pass. So, here we have crossed the thermal equilibrium point when these two Fermi levels were aligned. So, as you start pushing the metal work function metal Fermi level below, you will reach the point where it was, you will artificially recreate the thermal equilibrium point because you had to set Vg equal to 0. So, you are moving from Vg equal to minus 0.8 volts through 0, which is your equilibrium state, and now beyond 0. So, let us say we make it 0.1, 0.2, etc. So, we start increasing Vg. Okay. So, when Vg is greater than Vfp, the bands start bending the other way. So, because we are now pushing the Fermi level of the metal below the Fermi level of the semiconductor. And what happens at this stage? So, we are now started adding positive charge on the gate. So, when Vg was less than Vfp, we were adding negative charge on the gate, right. We were applying a negative gate voltage, and all this negative charge on the gate was balanced by the positively charged holes at the interface. But now, by making Vg greater than Vfp, we have started adding positive charge on the gate. So, how is this positive charge in the gate balanced? This positive charge in the gate is balanced by two mechanisms. The first is that the semiconductor starts getting depleted near the semiconductor insulator interface. So, that is the first reaction. So, what does depletion do? It exposes all the fixed negatively charged acceptor ions. So, this is a p doped semiconductor, it has got negatively charged acceptor ions and free which have given up holes to the semiconductor, and these negatively charged acceptor ions or the space charge starts getting exposed. So, this region is depleted. So, that firstly compensates for any positive charge that you are applying on the gate. And this bending of the bands begins to encourage the negatively charged electrons and encourages them to appear at the interface. So, you have two potential mechanisms, the negatively charged electrons and the negatively charged space charge, which is the negatively charged fixed acceptor ions in the semiconductor that can balance the positive charge on the gate. Now, the electrons will not appear till EF minus EI is going to go greater than 0. So, what does that mean? So, we have also shown the intrinsic Fermi level. So, this is the Fermi level after doping. So, you have the semiconductor, it initially had an intrinsic Fermi level position, and then after doping we shifted the Fermi level to a more p type semiconductor, and we are using the p type to create your MOS capacitor. But having said that, I have just indicated the intrinsic Fermi level. So, this is the Fermi level after doping and this is the aligned Fermi level, and we have also indicated the intrinsic Fermi level here. And that is it's a very good indicator, because if you recollect, your electron concentration is dependent on the exponential of EF minus EI by kT. So, it is only when EF is greater than EI will the electrons start appearing. So, as you are bending the bands, so for very low positive gate voltage, so let us say Vg is just slightly above VFB, the bands would not have bent to that extent. So, let us say the bending was only so let us say this is the Fermi level, and let us say the intrinsic Fermi level is just bent this much. So, EF minus EI is still negative in this case, EF and that is EI, EF minus EI is still negative, and therefore, you do not have so many electrons at the interface, but all the charge, all the positive charge on the gate is being compensated by the exposed acceptor ions. So, that is the depletion region. But the moment you make the gate voltage more and more positive, EF at some point will start bending more and more, EI will start bending more and more, and it will ensure that EF minus EI becomes positive near the interface. So, that is when the electrons start participating. So, in this case we have just made Vg slightly greater than VFP, and it is mostly the acceptor like ions that are being depleted, the semiconductor is depleted and it is exposed the acceptor like ions. But then, as I mentioned, if you make Vg much greater than VFP, so when I say much, it just simply means that we have managed to make the band bendings so large or so severe that if I were to imagine what the intrinsic Fermi level would be doing, it would have gone past the Fermi level of the semiconductor. So, EI has, so if you look at EI minus EF in the bulk, it is negative, but EI minus EF in the bulk is positive, and EI minus EF in the at the interface has now become negative, or in other words EF minus EI at the interface has become positive. So, at this point we will start encouraging electrons to start appearing at the interface, because the band bending is so severe. Now, where are these electrons coming from? There are no electrons in the p type material. So, the p type material has got very few electrons, it has only got Ni square by Na. So, these electrons are not they are not migrating, okay, definitely not. These are electrons that are thermally generated in the depletion region. So, we had this depletion region before heading here. So, we have these exposed acceptor ions, okay. You still have the depletion region here, but beyond a certain point electrons also start participating, and these electrons are thermally generated in the depletion region. Okay. Since your region is depleted, it encourages generation of carriers, and these are thermally generated carriers in the depletion region, and it is those electrons that start appearing at the interface. And now to compensate for the heavily positively charged gate, because your Vg is now very large. So, you have a strong positive charge on the gate metal. This positive charge is now compensated by not only the exposed acceptor ions, okay. So, these acceptor ions, the space charge, but also by the negatively charged electrons. So, both QNA minus and Qn start compensating for the positive charge on the gate. Whereas, in the previous case when Vg was just slightly greater than Vfp and Ei was not yet bent so much, it was only the acceptor ions that was compensating for the gate charge. Now, the bending could become more and more severe, and we could reach a point at some particular gate voltage, we reach a point where the Ei minus Ef in the bulk matches or becomes equal to the Ef minus Ei at the interface. Okay. So, what does that mean? So, let us say we define the Ei, this energy difference. Okay. So, let us say we say Ei minus Ef in the bulk of the semiconductor. So, bulk means very far from the interface. So, this region here, it knows nothing about the junction formation, okay, the semiconductors as it was. So, you have the Fermi level there, you have the valence band there, and you have the conduction band there. And this dashed line here, there are two dashed lines, okay, but the black one, if you can see it, is Ei. Okay. So, that is Ei. All right, and I will draw Ef as a continuous line just for clarity. So, Ei minus Ef in the bulk is, let us say we will give it a special symbol, we will call it phi f. Okay. So, we will say that this difference is let us say q phi f, q phi f. Now, at the interface the band bending has become so severe that Ei is bent to such an extent that Ei has gone below Ef. But there is a special point when Ei is as much below Ef near the interface as it is above Ef in the bulk. Okay. So, if you look at this difference, let us call this energy difference also equal to q phi f. So, let us say we have applied a gate voltage. At some particular gate voltage, the band bending is such that this difference between Ei and Ef, this modulus of this difference is same as the difference between Ei minus Ef in the bulk. So, let us say this is q phi f, and at some particular gate voltage this difference also becomes q phi f. Okay. So, at this gate voltage we say that the MOSFET has reached threshold voltage or threshold operation. Okay. So, this gate voltage, so just like how we defined a flat band voltage and we said that the gate voltage, when the gate voltage equals the flat band voltage, the bands become flat. So, that when Vg was equal to Vfb, the bands became flat, and when Vg is equal to the threshold voltage, you have this condition here. Okay, and the threshold voltage is given by a special symbol Vt, okay, and it is an important modeling parameter. Okay. And we say that when we build MOSFETs, we say that the MOSFET is considered to be on, or or it has got a significant current through it when the only after Vg crosses Vt. Okay. So, but Vt is not some kind of a magical boundary. It is not that the electrons are waiting in the background and saying that let us just wait and Vg has still not reached Vt. That is definitely not the case. It is just a very useful modeling parameter. Okay. So, for example, even when the band bending is here, for example, so let us say Ef minus Ei at the interface is greater than 0, but is still not equal to phi f. You still do have electrons, okay, and this region is supposed to be, you still do have a small number of electrons at the interface. Okay. And how many electrons do we have at the interface? It is quite easy to calculate. It is simply Ni exponential of Ef minus Ei by kT. So, you have that many electrons at the interface. Now, how many holes do you have in the bulk? Okay, so, that is the so let me just write this out neatly because it is okay. So, if we look at the, so let us say Vg is equal to Vt. Okay, so let us say Vg is equal to Vt. At Vg equal to Vt, the number of electrons at the interface, so the electrons per unit volume at the interface is Ni, which is the intrinsic carrier concentration, into exponential of Ef minus Ei. Okay. So, it is going to be basically your phi f, q phi f by kT. So, that is the number of electrons at the interface, the number of electrons per unit volume. What is the number of holes in the bulk? So, P in the bulk. Okay, so, how many holes are present here? It is Ni exponential of q phi f by kT again, because Ei minus Ef is q phi f, and at Vg equal to Vt we said that this difference is also q phi f, and hence the electron population is this. So, another way of defining threshold voltage is the gate voltage at which the electron concentration at the interface, the electron or the minority carrier concentration at the interface matches the majority carrier concentration in the bulk. So, that is another definition of threshold voltage. Okay. So, here we have a p type semiconductor, therefore, the majority carriers are the holes, the minority carriers are the electrons. So, when the minority carrier concentration at the interface, which means the electron concentration at the interface matches the hole concentration in the bulk, then you say that that Vg is equal to Vt. Okay, I hope this is clear. And what we have done now is, by making Vg much greater than Vfp, we have brought in electrons at the interface. So, you look at the previous case. So, here when Vg was less than Vfb, we had holes at the interface, and holes are the majority carriers, they were accumulated at the interface. And by making Vg much greater than Vfp, we have brought in the minority carriers at the interface. Okay. And therefore, the semiconductor insulator interface is said to be inverted. Okay. So, this is a technical term, inverted, and what this means is that we have brought the minority carriers of the semiconductor close to the interface. So, the interface has become populated with the minority carriers. Okay. And that is and we say, when that happens, we say that the semiconductor insulator interface is inverted, or the MOS capacitor is in inversion regime.